Alrighty, I think we can get started. Hi everyone, thanks for joining today's Smart Grid CRC Community of Practice session um, on adapting low carbon concrete specifications in New South Wales. The intent today is to keep this practical. Low carbon concrete is not just research or cafe conversation anymore. It's moving into specs, procurement. We're talking about project delivery and asset management as well. Meaning we need to understand not only the carbon targets, but also how these requirements transpire on real life on real projects. So we are lucky to have four perspectives in the room today: asset owners, academics, and the major contractor project delivery view from a contractor as well. A few housekeeping items before we dive in. This session is being recorded and will be shared with registered attendees. We kindly ask that you keep your microphone off while the presenters are speaking. We will hear from each speaker in turn and then open the floor for questions. But if you have a burning question during the presentations, feel free to pop it in the chat or hold it for the Q&A. Without further ado, I'll start with Alberto Jimenez Tobia, who is a senior project officer at the New South Wales Department of Climate Change, Energy, Environment and Water. DCCEEW. We all love acronyms. Alberto has over 5 years of experience working on sustainability in the built environment. His recent experience is in building capacity across government and supply chains to increase the use of low carbon concrete in New South Wales. Over to you, Alberto.
Thank you. So my name is Alberto Jimenez. I work within the New South Wales Government Department of Climate Change, Energy, Environment, and Water, or DQ. So my the department I work with, we don't buy low carbon concrete. We barely kind of draft this kind of sustainability advice and then try to create capability within the market. So as part of that discussion, has been working on creating the market for low carbon concrete here in New South Wales. Um, we our program, so we've been in this space for more than a couple years now. We started back in 2024. We look at concrete specifications and wanted to find out what is an adequate carbon requirement for concrete. So back then we reach out to industry, some kind of major suppliers in New South Wales, and we ask them about the performance of their existing concrete products. And based on that, we kind of analyze what is the carbon performance of those concretes available at that time, and based on that, we kind of developed or drafted a carbon requirement that could be achieved by the market at the time. As it was in 2024, based on, as I said, based on available and existing products. So we knew, as Professor Vute will tell you, that the use of fly ash-based low-carbon concrete is not new here in Australia. So that was very useful, but I guess back then we kind of struggle. I struggle personally. I did not know that how high can you go with the use of fly ash and or slag. Um, so because of that, Professor Wood reached out to us with this proposal for this research. And at the time in 2024, we partnered with obviously UTS, Professor Wood, but also the EPA, the Environmental Protection Authority in New South Wales, NDQ ourselves. And we kind of kickstarted this research project led by Professor Wood. And the aim was to identify what is the maximum amount of fly ash and or slag that you can incorporate into concrete without affecting its kind of long-term durability and performance. Um, Professor Wood has since then kind of worked on this research, and I must say it also includes a bit of industry consultation. So this is important because um, the research informed what is theoretically um, part of the research informed what is that theoretical maximum amount, but we also consulted industry because we're trying to understand what are potential technical and commercial risks in implementing this research. So we know that theoretically we could go relatively high with the use of fly ash and or slag, but that would have some other effects on kind of how low carbon concrete, this fly ash based low carbon concrete may have some impacts in potentially the workability, right? Like it may have a different fluidity and so on, potentially leading to some kind of smaller contractors needing to update their pumps and so on. Like, long story short, we identified there were some issues. So and based on that, incorporating the research and what we found from industry, Professor Vute finalized this research, providing a recommendation on the amount of fly ash that could be used and or slag that could be put into concrete without affecting its long-term durability, but also without affecting its kind of workability requirements, and as informed and kind of somehow endorsed by industry. So Professor Wood will tell you more about that research today, but from a New South Wales perspective, after that research, it really helped inform our next project, which is a low carbon concrete accelerator program. So this is something we'll be rolling out next. Is a capability building program supporting councils in the Hunter region and ultimately in New South Wales. To help them implement low carbon concrete, and acknowledging that there are different types of low carbon concrete. So you have, your polymers, calcium, clay, but in an environment where councils have limited resources to use low carbon concrete that might be slightly more higher in cost. We do have great examples of fly ash based low carbon concrete in New South Wales right now that it's available sometimes at cost parity. So in this discussion of kind of implemental low carbon concrete, fly ash based low carbon concrete is the one that the program will be focusing on for the next year or so. And I guess part of that conversation with council has been really we have needed to normalize the use of fly ash based low carbon concrete, and also kind of demonstrate its availability and cost. So really happy to hear a presentation from the presenters today to kind of demonstrate that availability and also feasibility of the low carbon concrete that Professor Vute has based his research on. That would be the end of my presentation. Next, Professor Vute.
Thanks, Alberto. Thank you so much. You set the tone for the rest. And the next speaker is Dr. Professor Vute Sirivivatnanon, academic lead of SmartGrid CRC's New South Wales Government Low Carbon Concrete Specification Project. Vute is a civil engineer, having worked for Main Roads New South Wales, CSIRO, CCAA, and is currently a professor of concrete engineering at UTS. Chairs Standards Australia BD2 subcommittee on design and durability. And if you have been with SmartGrid for long enough, Vute is a very regular name. Is part and parcel of SmartGrid. But he's not on his home turf right now. He's traveling to a different his Western Sydney University. So we also have his research fellow Dr. Liam Martin from his research team. So they will talk through the technical recommendations and the thinking behind the specification pathway. Over to you, Vute.
Yes, good afternoon, everyone. I just get my slides up. Is it working? Yes.
Perfect.
Yes, perfect.
Okay, thank you. Today I just want to update the progress of this New South Wales Government low carbon concrete specification. I acknowledged, I guess my team at UTS, Tran Vu and Liam Martin, who are our postdoc working on this project. Tran Vu have moved on since February this year. And thank you to the DQ, Alberto and Cameron Ross from EPA who supported this particular project. Now, what is low carbon concrete? I thought I started there. Concrete, of course, any concrete need to have good workability, need to have good strength volume stability for engineering applications, and perhaps most important of all, need to have the durability that provide the design life that designer are expected from their use. The only difference from that or the requirement for normal concrete is of the fact that we want to produce this type of concrete at the lowest possible embodied carbon. And I would only cover, I guess, the use of supplementary cementitious material in the production of low carbon concrete. The reason for that is quite clear. If you see the embodied carbon of the raw material, either the GP cement, fly ash, or slag, you can see that if we can introduce blended cement, cement with fly ash or slag, or with both for that matter, you can actually reduce the embodied carbon quite substantially just by the fact that fly ash and slag have much lower embodied carbon per mass of compared to general purpose cement. In this work, we basically have produced recommended 4 group of low carbon concrete. The first group that I would spend more time on is that of the Australian Standard 1379 normal class concrete. These are, I guess, the bulk of the concrete that is used for most applications. In identify this concrete, they also must meet the 1379 7-day strength requirement and also meeting all the requirements in the Australian Standard 3600 for 50-year design life. The second group, which I just mentioned, is that of, again, 1379, but in this case, special class concrete with special requirement. In particular, the requirement for early age constructability and durability requirement in 3600. The third group would also be special class concrete, but in this case, meeting the Australian Standard 5100.5 early age requirement, curing, prescriptive, and durability requirements. They are fairly, I guess, special requirements if you were to use concrete for infrastructure work demanding 100-year design life. The fourth one is mainly information for precast. I have to mention straight away that there are limitations to our recommendation, in particular concrete for post-tension slab. And the reason for that is that this type of concrete demand early strength, and that early strength depends very much on the location of the building and also the season, I guess. In winter, for instance, you would need a different concrete than in summer and so forth. The second limitation is for concrete for industrial floor slab, which demand very specialized concreters who handle this type of concrete. Now, this is how we come up with our recommendation. We look at, in the case of normal class concrete, the different grade requirement, different target strength, 7-day strength requirement, and then looking at a range of biosystem that we can, produce the concrete to meet those requirements. In our calculation of the upfront embodied carbon, we have basically based the calculation on the technical guidance for embodied carbon data book, which apply to, work in New South Wales, as well as for transport from New South Wales as well. So we use the same methodology to calculate our embodied carbon. And this is just to highlight what you can do, what you can save, in terms of the embodied carbon. If you look at the graph on the right, it shows you in terms of the embodied carbon of different biosystem in comparison to a general purpose cement system. And the saving, I think with fly ash and slag binary system, you can save up to 30% embodied carbon compared to a general purpose cement system for all the different grades of concrete. If there are availability of fly ash and slag and the plant are capable of handling three materials, you can then produce concrete with triple blend and potential saving of embodied carbon of up to 50%. Now, if you look at the plot on the left, that is the same information shown as embodied carbon and where they are with respect to CCAA low carbon concrete bands, from AA at the bottom up to band F. And you can see that for binary system, you can basically have your concrete at the embodied carbon level in band D, the lower part of band D, whereas if you are able to use triple blend, you can go down to band C, a significant improvement in the embodied carbon that you can save. And this is the recommendation that we have finally for normal class strength requirement, what embodied carbon, depending on whether you have fly ash, slag, or if you have both. The reason we offer this information is because of possible supply chain issue in various locations. So if you don't have slag and have fly ash, we have the recommendation for you, and vice versa. Many questions that came to us when we introduce all this was whether the supplier can actually supply this type of concrete. And we are so happy to see Metla low carbon concrete guide, which was released in February this year. And it showed that for the range of production by commercial concrete supplier, you can see that most of them are in the range of band D, the lower end, at 25 percentile. So this is for New South Wales. And just a comparison between the value we recommend versus the 25 percentile by Metla. You can see that they agree pretty well, which means that the concrete supplier commercially can supply the concrete with that range of embodied carbon. Very quickly, the second group is that of special class concrete. The special class is represented by S, and same thing. There are requirements for 3 and 7 day according to the construction requirement of 3600. Whereas if you go for next one, this special class concrete, that also meet all the requirement in 5100.5, 3-day strength, 7-day strength, 14-day strength, depending on which grade and the range of embodied carbon that you can ask for. The fourth group is an attempt to give precast a bit of information. for a particular curing regime that I show on the top left-hand side, the sort of early one-day strength that you can expect from those different normal class concrete are given there for precaster. So in conclusions, low carbon concrete can definitely be specified in terms of embodied carbon for various grades of concrete. Industry is in a position to supply low carbon concrete as seen update in the METLA guide. We have done lab and field test with recommendation to the update of 3600 and 5100.5 for cover requirement to make sure that carbonation-induced corrosion will not be a problem once this type of concrete is implemented. So this is where I will stop. Thank you very much.
Thanks a lot. That's a really good presentation, and a shout out to MECLA, who's been doing some great work in the low carbon space. And they, as you mentioned, they recently released the carbon graph. For anyone who's interested, they have all the information available in their website as well. Moving on to the next speaker, Farzad, Dr. Farzad Moghaddam from Sydney Water. He's a materials and sustainability expert with over 20 years of experience in the construction and infrastructure sectors. Also serves as president of the Concrete Institute of Australia, New South Wales, and ACT State Committee, and is an industry professional fellow at UTS. Will bring the asset owner perspective across materials, durability, sustainability, and practical adoption. Over to you, Farzad.
Thanks, Aaron. Thank you so much for the introduction. Let me share my screen. Can you see my screen?
Yeah, perfect.
Okay, great, awesome. So, hi everyone. Thanks for giving me this opportunity to present what we are doing in Sydney Water. So, and thanks to Alberto and Professor Vute for their great presentation. Honestly, we are very lucky to have people like Professor Vute in the industry to pushing the boundary of using this sort of the material. I'm very grateful, and he also helped me a lot in what I'm going to present. So I mean, just let me move on. So I mean, before I just move on to the detail of what we are doing in Sydney Water, you all know about why sustainability matters in concrete. But as you know, concrete is the most used material in the world, and 8% of total emission kind of related to the concrete. And the reason, as we discussed, is the most used material in the world. So, but if you look at the 1 cubic meter of concrete as a material, maybe just only about 15 to 20% is cement as by weight, but is responsible for more than 80% of that embodied carbon release for concrete. And the reason, as you know, in cement production, you're burning limestone, which emit a lot of carbon dioxide. So we can't do anything about that because at the moment is the only material that we use for making cement in limestone. So, and that is kind of responsible for 60% of that emission, and the rest is fuel and electricity that we are using for making cement. Maybe we can do something about that 40%, but about that 60% that we burn limestone, we can't do that much unless we replace cement with something else, which is SCM, supplementary cementitious material. So I think is our best bet at the moment. So in the right graph in my presentation, you can see is the total emission from Sydney Water. And you can see that scope 3 is responsible for, let's say, two-thirds of the emission in Sydney Water, which is the supply chain. So, and this concrete is one of the main one in that area, and that's why is that showing the scale of opportunity in the industry. So, and in terms of the performance, you already, I mean, Professor would already explain, and you already know about that. Comparing conventional with the low carbon concrete, you can see the conventional concrete has a high embodied carbon compared to low carbon concrete. But at the same time, there is this misconception in the industry that some people thinking when they're using the low carbon concrete, they losing the durability, they're missing out in durability criteria, but it's totally some misunderstanding, because durability improve drastically in most of the area except the carbonation that mentioned. And the only thing that we should be careful is the early age strength requirement. So in that sort of area, if you need the early age strength, we need to consider maybe lower percentage of SCM replacement, or I don't know, maybe activation, or there are also other options that we can consider. So what is the most at the moment effective approach? So we can use to reduce embodied carbon in concrete. So as we discussed, the best way is replacing cement with SCMs. So we should move toward that area. And what we can do, so the best approach is, but one of the barrier or the challenge that we are facing in doing this is prescriptive specification, because most of our specification that is available in the industry is prescriptive. They are giving us some prescriptive requirement, like a maximum cement content, minimum cement content, maximum water to cement ratio, those sort of requirement that stop innovative mixes, stop supplier to come up with something that has less embodied carbon, but at the same times, perform the same. So it is something that is the challenge at the moment. And the opportunity is we should move toward the performance-based requirement. We need to change the mindset. We need to come up with performance requirement, is just come up with something that let supplier to come up with better mixes, let the industry use the most, get most out of the current mixes available in the market, because if we have those prescriptive requirements, so how we want to push the boundary in terms of pushing for using more low carbon concrete. And this is something that we should consider. We should move toward changing a specification, and this need to come up from Sydney Water, TFNSW, government bodies. So if we start doing this, so it start going through the industry as well. So and also one of the things that it's very important when we moving to more low carbon concrete is supporting those, having the transparent data in terms of what is the embodied carbon of those mixes, which can be calculated, and we can verify those data by environmental product declaration, which we call it EPD. So there are lots of EPD available. For most of concrete suppliers have EPD for their products, so it's not something new. So we can use those information available in the market. So moving to Sydney Water, at the moment in our current spec, we still have some prescriptive requirement, as you can see, maximum, minimum, we have some maximum water to cement ratio, but also we added a couple of 2 years ago, I think, we added maximum embodied carbon column for maximum cementitious material, embodied carbon for cementitious material. So we're pushing a little bit in terms of the controlling, pushing supplier to come up with more low carbon concrete. Also, we have at least use of 40% manufactured sand at the same time. And also at the moment in our spec, supplier only can use up to 25% fly ash or 50% slag. There is current situation in our spec, but we are trying to change, and we are trying to move toward letting supplier to have more freedom in terms of the using more fly ash and slag, which in our next revision, they will be able to use up to 30% fly ash and up to 60% slag, which is we are pushing a little bit the boundary in terms of maximum embodied maximum cementitious material. And also we are changing this column. We are going to come up with maximum maximum embodied carbon for 1 cubic meter concrete. So which I explain in the next slides. So as discussed with Professor Wood, we are lucky we have GCCEEW come up with some banding for maximum embodied carbon for different grade of concrete. So, and the CCA also adopted that one for Australian market, and also considered the higher, more strength grade for Australia. At the same time, MECLA also did a great job, as discussed, come up with the considering whatever available in the market and trying to put those based on the EPD available. You can see that, for example, in New South Wales, they look at 1,375 product, which has a EPD for different grade, and they come up with putting those EPD in those banding and see where we are at the moment based on available concrete, low carbon concrete in the market. So in terms of what we are doing in Sydney Water, as I said, we in the new version of our spec that would be released in a month or two maximum, we, based on the banding available for CCA and MECLA, and also what MECLA did in terms of the, look at the benchmarking for New South Wales based on available data, we come up with a column which is here, the maximum embodied carbon for 1 cubic meter of concrete from A1 to A3, which kind of sits based on also and also using the information that Professor Wood and the Smart Grid did and provided those information to us. So we review all those data and we come up with this column at the moment, which is we come up with each grade maximum embodied carbon, which this need to be supported by EPD. So, and this kind of sit in the 25 percentile of the market, which is honestly is a really good number at the moment, but we are trying to push this number for the next version by changing towards some performance-based requirement, which we are doing at the moment in a project with the Smart Creek and Sydney University, trying to understand how we can come up with this requirement. So once we change our spec to the performance requirement, we can change these numbers, because there is a certain, because we cannot push a lot with the prescriptive requirement, we need to change to performance and change, then we can push this number further. So this is something at the moment in the next version of our spec is coming out. And this is something that we are very lucky. We are a very good major project and sustainability team in Sydney Water, and trying to, and also they are pushing this, really great in our project already. So in conclusion, as discussed, we can push for low carbon concrete, but we should always consider, there is a carbon, there is a balance between carbon reduction and durability and whole lives of asset performance. We shouldn't forget, we don't want to supply a concrete for a project with a very little carbon, but at the same time, in a couple of years, in 20 years, in 30 years, you need to go and do something for repair or changing, or demolish that building, bring a lot of cost further on. We need to make sure that the performance and the carbon reduction, there is a balance between these two. So, and honestly, the pathway is to low carbon concrete is very clear. Focus on performance, manage whole life cycle risk, and enable innovation as well. I think it was what I was planning to present today. I hope I stick to my time, hopefully. Thank you.
Thank you for that. Yeah, very well on time, and it's a very important message from an asset owner, right? Asset management is to have a holistic approach of sustainability, not just what's the percentage, what's the carbon rating is to see how long the structure survives and all that thing that comes with being able to manage and look after an asset. And Dan in the chat also mentioned about the CCAA rating system was launched in December 2025, which has been adapted by MECLA, and CCAA specifically designed it for Australian standards, set for Australian-based concretes, compared and from the GCCA a global edition version of it. So yeah, I think they have it in the website as well, in CCAA website. So there's the access to knowledge is everywhere. That's very clear. The final presenter we have is Andrew Durant from Laing O'Rourke. Will share a project delivery and a contractor perspective as a specialist role in Laing O'Rourke's technology and innovation group, connecting infrastructure project teams with the supply chain to collaborate on materials innovation and decarbonization initiatives. He has previously worked in product development and procurement in the building products and construction material sectors in Australia, and before that specialized in geothermal cementing chemistry research in New Zealand. Andrew, over to you, man. You're on mute, Andrew.
Yeah, sorry, just unmuting myself.
Yeah.
Thank you for the intro and everyone for your time. Okay, so I'd like to start here. Just Laing O'Rourke, we are what we call a head contractor in Australia. And I like to sort of set the scene for our kind of perspective and level of influence on concrete decarbonisation. So the asset owner is effectively our client. We tender competitively to win the opportunity to construct an asset for that client. We partner with a designer, and then we are the customer to the supply chain. So we work with the designer to figure out how to build something, and then we engage the supply market and subcontractors to assemble it all together. Now, typically the asset owner will set the technical specifications. So that might be a concrete standard or specification that must be adhered to. The designer will then specify what concrete needs to be used. And then it's really, in many ways, over to us as the customer of the concrete supplier to ask them to supply the lowest carbon concrete that is allowed within those boundaries. This is old news now, really, but we've very much moved on from talking about low carbon concrete in terms of its percentage of fly ash or slag, and we have the data now to work on an embodied carbon basis, which is fantastic. And as an example to how important this is, there's one of the major concrete suppliers in Australia for their cement supply into Victoria is shortly later this year going to announce a 12% reduction in embodied carbon in the cement, and that's simply by getting an EPD done rather than using generic factors. So that's going to translate to a really significant reduction in the embodied carbon of concrete that has absolutely nothing to do with supplementary cementitious materials. So really, really great that we're moving into this more performance kind of focused language around carbon. So one of the things I'm talking about now is how we, Laing O'Rourke, as a contractor, a few years ago now decided to set our own guidelines for low carbon concrete in Australia, because at the time we didn't have the benefit of what we do now with the work that has been done by MECLA and the CCAA. We looked at what had been done overseas and thought about, well, how could this work? We did want to avoid complexity and focus on the simplest and easiest to execute structure for a low carbon concrete guide. And this really it was important that the messaging was simple for people to pick up. A few years ago, the concept of GWP, global warming potential, scope 3, and body carbon, this was all new stuff to people, and we didn't want to kind of overwhelm everyone with layers of granularity and complexity for which we did not even have the data to support. So we wanted just a nice national limit, consistent measure. This is now a very familiar structure or basis for how these guides work. Embodied carbon goes up as concrete strength goes up because you use more cement to increase the strength. And generally, lower embodied carbon is always better. So the question really was, well, where do we draw the line? And we engaged our suppliers. So this is where we had the benefit of being the customer of these major concrete suppliers. And so we were able to receive from them a real richness of data that was both embodied carbon but mixed constituents for 3 years worth of all the concrete we had used nationally across Australia. So our ability to develop our own concrete carbon limit was enabled by supplier investments in carbon calculators and EPDs, in particular process EPD capability, which is where they can generate a GWP for any concrete straight out of the system. It doesn't have to be a published glossy PDF of 30 pages or so. And this is what we came up with. Developed in 2003, published early 2004. Quite simple, national, very infrastructure focused. So almost most of the concrete we use in infrastructure is 40 or 50 MPa. And so that was really our focus. That's where we had most of the data for. We set 2 limits, an upper threshold, a maximum, that's our carbon limit. And then while we were there, we thought, well, let's come up with a lower number to have a consistent measure for reporting low carbon concrete use. And we call that our low carbon concrete definition. Now, the important part is, yes, we had those numbers, but it was embedding them into our procurement processes. So when an engineer on our project goes to order concrete, or our procurement team is setting up a big supply agreement for a major project, those carbon limits are appended to that order along with bill of quantities and those technical requirements. You know, what strength does it have to be? Well, also for that strength, it's going to have to come in below this carbon limit. Now, we were pragmatic about this. While it is a concrete carbon limit for most concrete, we were very sensible in making some very clear exemptions. For example, pre-stressed concrete for example, Super T bridge girders. That's quite a unique case. We knew the market wasn't there, and therefore that very high carbon concrete was exempted from needing to comply with our concrete carbon limit. So we introduced this. It's given us a great tool for reporting. The data feeds directly into our Scope 3 reporting because it's already on the same basis. You couldn't do that with percent SCMs, for example. And I do want to say we found this really embraced by the supply chain. For the first time, we were very clear what we were asking for from our suppliers, and some of them saw this as a challenge in some cases, and you know, very much did the work to meet that challenge. So here's an example. This is a current live project in Sydney. This is the St Mary's Station footbridge. It connects the new metro line with heavy rail and St Mary's, starting to prepare for that sort of more seamless transport integration out to the new airport in Western Sydney. So it's currently under construction. However, we collaborated very early with our concrete supplier and also with our design partners to treat this rail project as a low carbon exemplar. Let's do everything we possibly can within the boundaries of the specifications we must construct to produce an asset, to deliver an asset with the lowest possible embodied carbon. So all the concrete used on this project is compliant with our concrete carbon limit. That's the upper level. But even better than that, most of it, more than 90%, meets our low carbon concrete definition. So a couple of little tricks we did with our designers along the way. was play around with exposure class settings. So if you're not familiar with what that is, it's to do with the durability of the concrete. And anyone working with concrete knows that there is a relationship between durability and low carbon. So by tweaking the durability requirements through exposure class, we were able to reduce the carbon of certain concrete elements where we otherwise would have had to have used higher carbon concrete. And the other thing we did, we engaged very early with our concrete supplier, and we got them to have registered new mixes with the maximum allowable amount of supplementary cementitious materials for use in transport infrastructure in New South Wales. So they maxed that out at 70%, which is the upper limit of Transport for New South Wales specification for bridges. And that's where the project's currently at. That's a very, very recent photo. Again, that's the St Mary's Station footbridge project in Western Sydney. You've just seen this. This is great news. We're fast forwarding now from when we came up with our carbon limits, 3 years ago, and now what we have is a very simple and standard reference point for talking about concrete and carbon in Australia. So in December last year, 3 things happened all on the same day. The CCAA, Cement, Concrete and Aggregates Australia, launched the Australian adoption of the global ratings for low carbon concrete. That's that chart there. MECLA updated their concrete guide to align entirely with the same set of numbers. And Laing O'Rourke, we updated our concrete carbon limits as well. So what we have now is a common language for asset owners, design and construct teams, and the supply chain to all be referencing the same target with respect to concrete and carbon. So we now have the luxury of the full spectrum of strength, standard specified strength grades in Australia, and we've evolved from our in-house developed numbers to using and leveraging the new industry standard for embodied carbon in concrete in Australia. Ours is the top of the D band, which is that blue, the upper blue of the CCAA guide. So we now have the numbers, but I think frankly, more important than whether a limit is 320 or 325, it's how you put those numbers into practice, how we use them. And what we're now starting to see is, in addition to just having our own business rules as Laing O'Rourke, we're starting to see carbon targets set as contractual requirements by our clients. And there's different ways these targets can work. Some are simpler to implement, some are more complicated. We can simply say all concrete must be below or meet a certain rating, or we can get a little bit more flexible and say most concrete must meet this rating. We can have an average target, which gives the constructor a lot more flexibility in what they can do. Or we could say assign different ratings as targets for different types of concrete. So that very difficult to decarbonize pre-stressed precast concrete, we could give a higher target to than say for foundation and substructure, where it's typically easier and more standard to use a lot of SCMs and therefore have low carbon concrete. So the way the average target might work, and this is something we're seeing now in real projects in infrastructure in Australia, is the fact that for a given strength grade, we have an average target, and this allows higher carbon elements to be offset by use of more lower carbon concrete. Now, it does require us to be strategic in our approach. We can't simply pass this on to the supply chain. We have to really plan and track the use of concrete across the project. Now, you might note I've put precast in the middle there, sitting halfway between low and high carbon. And precast is always this perennial bugbear when it comes to trying to use low carbon concrete. We have this, we keep hearing from the supply chain, no, sorry, we can't do low carbon precast, it's too hard. The main reason for this, Vute touched on earlier, is to do with early strength gain. And the reason that's important to the precast industry is because they need to churn these things out fast in order for themselves to be commercially viable. So lower carbon concrete traditionally developed strength slowly, although there are certainly ways around that now. And I'll give you an example from, again, a live project. This one is not in New South Wales, it's in WA. This is concrete that's just been, the surface has just been finished in a mold, and it has what I think is a fantastically low embodied carbon for its strength. It is a C rating on the new CCAA MECLA guide numbers, and I will say it's closer to B than it is to D. This precast concrete was not steam cured, no external heat was applied, and the next morning, in less than 18 hours, we're stripping these things. As you can see there, these are the precast concrete segments made with some very low carbon concrete. And what do we do with them? Well, we make quite a lot of them. As a Kiwi, that's not a number I'm going to say out loud, but we made quite a few of them and connected them all together to build this. This is a new road bridge over the Swan River in Perth, connecting Perth City to Fremantle. And those girders are all along the edge there, made with very low carbon precast concrete. And with that, I just want to say it can be done. Thank you for your time.
Thanks a lot, Andrew. That's a really good presentation, and for what is what, I work for precast, and I can definitely share the sentiment that that introducing low carbon practices in the precast industry is harder than, generally harder than in doing it in situ, and that brings us close to our presentations, which gives us sufficient time for questions. The good thing about being a chair of an event like this is you get the chance to ask the first questions. So I'm going to be so I have a common question across the board, and that would be, we are talking about supplementary cementitious materials and different sorts of alternative binders, but that is also very much location dependent, right? So New South Wales, of course, is blessed with good waste fly ash compared to Victoria and South Australia, and then different states look at different solutions. How do the procurement team look at this, and when it comes to especially the specifying stage and the procurement stage, how do they work with different sorts of supplementary cementitious materials and the transport that comes with it? We can throw this question to Alberto. Or...
I guess just kind of maybe like acknowledging the maturity of their practices. I think as of current, I think procurement teams haven't gotten at that level yet. Some kind of considerations were made as part of the research. Professor Vute insisted that we acknowledging that access to fly ash might be limited in New South Wales, but also in Australia. Professor Vute insisted that the research also considered the use of slag as an alternative. Say there is no fly ash in your region, do you have access to slag? So that was one consideration made. But yes, I think currently, I think we just state that is kind of performance-based specification. So I guess in a way we are agnostic of the use of SEM.
Thanks for that, Alberto. And our questions in the chat from Glenn Hedges. I think this is for Vute. What investigations have been undertaken on non-cementitious components of concrete for carbon reduction opportunities? Wood slides 3.
I presume that Glenn possibly referred to the alkali activate binder system or the geopolymer concrete system. I presume that's the questions. because that table also show, I guess, the embodied carbon of the alkali activators and so forth and so forth. I think at Smart Grid CRC anyway, and at many universities, of course, there's been a lot of work done on geopolymer concrete. We have looked at it from the viewpoint of performance and in relation to the embodied carbon. Our general conclusion is that if you were able to produce geopolymer concrete, especially from slag, unfortunately, I guess, for fly ash, you're likely to reduce the embodied carbon to band C of the type of concrete that we are looking at. So currently, you can see that we are in the lower part of band D, whereas if you have triple blend mixes, this is conventional concrete, you can come down to band C. Whereas if you were to use geopolymer concrete, you're most likely to be able to come straight down to band C immediately.
Well, this would open up a performance-based specifications, I would assume. Or
yes, in a way, if you are familiar with Standard Australia Technical Specification 199, provision has already been given in terms of performance-based specification for alkali activated biosystem or geopolymer concrete.
And on a side note, AS 3600 is open for public comment as well. While I have you there, what can we expect for low carbon concrete in the draft?
The main update in to I guess prepare for the use of low carbon concrete in the section 4, design for durability. In particular, I guess we have clarified exposure A1 and A2. For A1 to be exclusively for indoor exposure, where there is no readily availability of rain and water and so forth, which may affect corrosion, carbonation-induced corrosion. Whereas A2 has been specifically for outdoor exposure where there would be source of water and so forth. So in anticipation for the use of low carbon concrete, we have recommended the increase of cover for exposure A2 by 5 millimeter for the different grade of concrete. So the 3600 is out for public comment at the moment. I forgot the closing date, but certainly something that people might want to pay attention to.
Yeah, thanks for that, Vute. And I have a question from Hani Habib. Is to Farzad. Have you considered using recycled crushed glass as a fine aggregate or recycled concrete as coarse aggregate to reduce embodied carbon content? And probably where would that concrete sit in the graph that we are looking at through CCAA and MECLA? And the second part is, apart from the strength and carbon content, what are the durability requirements for performance-based spec?
Yeah. Thanks, Aaron. I was in the middle of writing to response to this message. Yeah. So honestly, using this sort of recycle aggregate or glass and things, at the moment, because changing the spec is really takes a lot of time to change the spec, but we are using this material as a project base, because in our major project we are using we are doing a lot of initiative, and we do such things in specific projects, and specifically for like a recycle glass or recycle aggregate, we are using for like a pipe embedment or like a non-structural application at this stage, but not in concrete. So it is what at the moment we are doing. But in terms of the second question was about strengths and embodied carbon. I think in terms of what other criteria we need to consider shrinkage, durability requirement, specifically exposure condition, like a core. And also based on the exposure condition, we need to come up with those durability requirements like a chloride ingress, sulfate, carbonation, or those things need to definitely need to be considered in performance spec as well.
Liam, you have your hands raised. Do you want to add something?
No. I just had a question for Andrew about his comment with the St. Mary's station. It's okay.
Yeah.
Andrew, you mentioned that you were about the durability requirements and exposure classifications for particular parts of that segment, and about maybe it came across to me a bit, but you sound like you were more manipulating or being very hyper-local in terms of the durability requirements for each part, and that allowed you to reduce the embodied carbon, focusing on the classification. Just wanted to ask if you could speak about that or confirm.
Well, I'll tell you what we did, and it's probably a little bit of background here, but that project is not built to Australian standards. It's built to a client specification, which is Transport for New South Wales P80 concrete bridges. And there's two main exposure classes we would typically build to in that part, away from the coast, which are termed B1 and B2. 2 being a higher exposure class. Now, the constraint is around the B1 exposure class, where the specification requires a minimum GP cement content, which B2 doesn't. So by moving from B1 to B2, we are able to reduce cement a lot more and replace it with SCMs up to what's allowable for B2. Does that make sense?
No, it does. It does. Thank you, Andrew.
Yeah, thanks, Andrew. And a question from Dean Chapman's always been a question of mine too. How is risk allocated between the asset owner, contractor, and the supplier when using performance-based specs? How can councils be confident that a performance-based spec will achieve the expected asset life? And it's very much related to any low carbon concrete. Who assumes the risk, basically?
I can answer this question if you want.
Yeah.
I mean, at least from my point of view, if you are using the prescriptive requirement, I mean, what is the risk at the moment? We're just checking the strengths. We don't know anything about the performance of the concrete. At the moment we are facing a lot of risk that we are not aware. Honestly, if we move to the performance-based requirement, we know the concrete much better, and we're definitely confident about the performance. But we are not at the moment. It is, I think, that's why the performance requirement is fit for purpose. We know exactly what we are looking for, and when we define that requirement, so we are definitely sure that it's expected. You can expect it whatever asset life you are looking for. It's my view.
That's a really good thought, Farzad, because if we normally use standard concrete, we only use slump and the strength, and that's it. As if you have a specific, and especially with Sydney water, I can see there's more chloride ingress, corrosion related specs that you would like to see before you really use the concrete and stuff like that. That's really interesting. Andrew,
because sorry, before I move on, and prescriptive, you have maximum, minimum cement or maximum water cement ratio. How you want to check that one in reality? Who want to check how much cement is in that concrete?
Yeah.
So there is no way we check that one. But for performance requirement, you can check that one. So something, yeah.
I agree. And Andrew, do you have any thoughts on this from the contractor view?
Look, a couple of things. I mean, firstly, we're not there yet. We're not building to performance-based specifications. So AS 3600, AS 5100.5, AS 1379. They're all hybrid prescriptive performance. So we don't have a pure performance-based outcome yet. I think ultimately risk is owned by the asset owner. The constructor DLP is typically a year, design risk is 6 or 7, and then if it's a 100-year design life asset, then that's on the asset owner. But it's also possibly a party that gets missed in that thinking is the asset owner's insurer, if they don't self-insure. And if an asset is insured, then the insurer needs to be involved. I have seen, not in Australia, but in other places where they do have very, very much performance-based concrete specifications. So they exist and it can be done, but we're certainly not doing it just yet in Australia.
While I have you, Andrew, there's another question for you from Glenn Hedges. Thanks for your presentation. Any lesson learned on suggestions on how projects can adapt CCAA's ratings and engage the supply chain to systemically reduce concrete carbon footprints?
Yeah, well, ultimately, if squeaky wheel gets the oil, right? You just ask for it, and supply chain tend to come along with that. It's obviously it's a little bit more administrative for us than that. Our requirements again come from our client, and so we have to interpret those requirements around concrete and carbon and sustainability targets. So there might, for example, be some very concrete focused carbon requirements, but then often sitting above that is a total greenhouse gas reduction target for the whole project. And so we kind of have to go away and consider our approach and how we might ask the supply chain to work with us to deliver that. But I think ultimately, a B is better than a C, and so encouraging the supply chain to go as low as they can. People often ask, well, what about the cost impact? Now, one thing I think we could say, especially when we're working in transport infrastructure, is that if the embodied carbon is a requirement, then there is no additional cost. It's like saying, why does 50 MPa concrete cost more than 40 MPa? If the requirement is for 50 MPa, then the cost you get that from a market tendering competitively to supply that concrete. It's the same thing for carbon. The embodied carbon has to be within the D rating of the CCAA, then the cost that the market competitively tenders in the response for that is the cost. So in some ways, it doesn't cost more. It's simply that's what the requirements is. So I think, it's a bit of a long-winded way to say just ask for it and be clear what you're asking for.
That's a good answer, Andrew. And I probably have one last question for Alberto before we wrap it. And Alberto, I think from a government viewpoint, you have more lever to pull than many other players in the industry, and to make this adoption easier for the government bodies like councils or state agencies, what would you think in the next 12 months would be the would need to happen to make this adoption more easier? It's not just in New South Wales, across all the states. I'm sure New South Wales is leading this, and I've done a lot more. But across the states, if something needs to happen, and what is the biggest lever you think?
Yes, so I will maybe point you to the Infrastructure New South Wales Decarbonising Strategy policy, which I think agencies, New South Wales government agencies are large users of low emissions building materials. So as such, out of that Infrastructure New South Wales Decarbonisation policy, they start asking these agencies to manage and reduce the embodied carbon of their assets. So with that policy, there's a set of kind of measurement frameworks and practices that I understand are being taken at a national level. So And you would expect these frameworks and practices to start trickling down and inform the strategies by different organizations. You have councils, private business, at least in terms of setting the ambition. Then when you look at an actual, so like I would expect that to continue trickling. Then in terms of an actual target for low carbon concrete, there is no such carve target yet. I think government is currently kind of identifying like what are baseline, what is existing practices, what existing products, what are the baselines, and based on that, just kind of start gradually improving over time. So I think I would expect, at least from the councils that we're planning to engage, that we help them set up the processes and the mandates to manage and reduce Scope 3 emissions. And out of that, you see this kind of growth towards start measuring what is the baseline, and gradually improve and start drafting some sort of targets that can be gradually ratchet up over years. So I think maybe that's what I'm looking forward to in the next 12 months. Getting a good sense of what products are available, form a baseline, and then just kind of through that mandate to manage and reduce, set up a gradual improvement over time.
Yeah. Thanks for that, Alberto, and thanks everyone for all the questions that's in the chat, and thanks for the speakers and Alberto, Vute, Liam, Farzad, and Andrew for sharing different sides of the story, and also I think we were supposed to finish at 1:30, but we have been gone 10 minutes extra. Thanks for hanging around and answering all the questions. Really appreciate it. The big takeaway for me is that it's not just the specs, so just the catch up and chat anymore. Low carbon concrete is real and in practice, and is doing its rounds in big projects, and always benchmarks against it. It's not just claims of 15% or 30%. You have to we have standardization that follows, and it's really interesting to see how it is coming up. It's exactly the kind of conversation we would like to have in a smart grid community of practice, and we should continue to have these conversations and pass down the knowledge that's being created. And for any follow-up questions or collaboration opportunities, please reach out to Smart Grid CRC, and Natalie has left the email in the chat, and they'll help you connect with the right people. And if you have any questions or any other thoughts, feel free to email us and let us know. Thank you. That's it from us today, and enjoy the rest of your day.